In 1999, I had the pleasure of meeting Don Visco here at Tennessee Technological University, where we both worked for 10 years. For the first 6 years, I'd been carefully watching and listening to Don and his students present on what they called the signature molecular descriptor and computer-aided molecular design. They'd been designing new drugs and environmentally benign chemicals for various applications. I'm mostly an experimentalist. I'm interested in hydration of Portland cement, that is, the way that water interacts with Portland cement and the hydration outcomes. I knew that eventually I'd find an application for Don's signature molecular descriptor and computer-aided molecular design. I'm Joe Biernacki. I'm professor of chemical engineering at Tennessee Technological University. It took a bit of pondering, but about 4 years ago, I thought, what if we can use computer-aided molecular design to discover new admixtures that would alter the way concrete performs, new chemicals that would change the way concrete actually performs in the field. That thought eventually became the present National Science Foundation collaboration between myself and Don. Concrete is the most used material on Earth by weight. Roughly 1 ton of concrete, about as much concrete as in this block here, is used for every man, woman, and child on Earth every year. Concrete is strong, formable, and inexpensive, and can be cast on site into virtually any shape. While concrete is a robust and adaptable building material, it is not without its own set of problems. Okay, so the primary raw material for making Portland cement is limestone. Limestone is one of the most abundant materials on the Earth. It's a chemical combination of calcium oxide, a solid, and carbon dioxide, the gas that produces a greenhouse effect and is warming up our environment. It's the calcium oxide in the limestone structure that we actually want. Unfortunately, a huge amount of energy is required to release the carbon dioxide and to extract the calcium oxide for making Portland cement. In fact, about 1 ton of carbon dioxide is released for every ton of Portland cement produced. That amounts to about 7% of the total world's emissions of carbon dioxide each year. Not only does concrete production produce a lot of greenhouse gas, but there are many ways that concrete can fail, many ways that are happening right below our feet. Chemicals from the environment can get in and cause changes to the structure. Water can get into the many pores and cracks of the concrete and freeze, causing further damage or new cracks to form. And concrete even shrinks, and that shrinkage can cause cracking and damage as well. If we can make concrete perform better in the field, make it stronger and last longer, ultimately we can use less total energy to produce this important infrastructure material, thereby releasing less greenhouse gases into the environment, and that's good for us all. Although concrete can be mixed on site, most concrete today is mixed in ready-mix plants like the one behind me. Let's go inside. We're inside the Builder Supply ready-mix plant in Cookeville, Tennessee. This is where the commands are given to batch the concrete. Modern concrete is no longer Portland cement, aggregates, and water, but virtually every truck that leaves this plant includes some form of admixture. Admixtures can actually alter the properties of concrete. Some will make the cement harden faster, some will make it harden slower, some will make the concrete more workable, some might actually prevent concrete from shrinking and cracking, and yet others could prevent damage from freezing of water in the porous structure of the concrete. Likewise, there are many different chemicals that are used as admixtures. This is ordinary table salt. It'll make Portland cement harden or set faster. This is sugar. Sugar is a powerful set retarder. It'll make Portland cement set or harden much, much slower. These two chemicals are specially formulated to be used as admixtures. Both of these reduce shrinkage in hardened concrete as excess water evaporates. So how do scientists design new admixtures? Ones that perform better than these, or others that are presently known. This is sodium chloride, an inorganic molecule. This is sucrose, an organic compound. Both of these alter set. Sodium chloride accelerates set, makes Portland cement set faster. Sucrose retards set, or makes Portland cement set or harden slower. Another organic compound, 2-propoxyethanol, actually hardly affects set at all. Instead, it's used to reduce shrinkage. It turns out that the structure of the molecule affects its performance, not only in this application, but in virtually every application. So which jar of chemicals should I choose if I want to make cement set faster? Which should I choose if I want to make cement set slower? Which chemical will stop or prevent concrete from shrinking? And just how many chemicals do I have to choose from? The number of stars in the universe has recently been estimated to be 3 times 10 to the 23rd stars. So how large is the compound universe? That is, how many compounds might there be? It turns out that the number of possible chemical compounds is 10 to the 60th. So many, many, many times more compounds than are stars in the universe. So if one were searching for a compound that had a particular effect on something, let's say mitigates the effect of Alzheimer's disease, or reduces the amount of shrinkage in concrete, how would someone pick from among the 10 to the 60th possible compounds in the compound universe? When searching for new compounds for a particular application, it's always good to have a few that you know work and a few that you know don't work. This group we call the training set. In most cases, new compounds are formulated using heuristics or rules of thumb, knowing how this compound behaves versus another compound with a slightly different structure. This compound retards more than this one, so one might expect that this compound would retard even less, but it doesn't. This form of heuristic or rule of thumb based approach is costly, slow, and usually only produces incremental results. If you want a game changer, you have to think outside the box. The approach we use, however, looks to examine all of the smaller molecular fragments of the compounds in a training set and assigns a certain value to how much that fragment helps or hurts your target value of a desired property. This approach is called a structure-property relationship since it relates the property of the compound to its structure. The fragments or smaller parts of the compounds we use are obtained in a systematic way and are known as atomic signatures. When we optimize our structure-property relationship to give us predictions on how molecules will perform, we call this a quantitative structure-property relationship. Our approach to obtain new game-changer molecules is to mix all of those smaller fragments or atomic signatures together to form new molecules. Then we predict the properties of these new molecules using our quantitative structure-property relationship. This approach is called inverse design using the signature molecular descriptor, or computer-aided molecular design using signature. The design molecules with the best predicted values or scores are the ones we're most interested in. One key step in the inverse design problem is the development of the initial training set. This is important since we cannot begin to look for our game changer molecule among the 10 to the 60th compounds that exist.
One of the most relevant physical properties that define substances that are candidate shrinkage reducers is surface tension reduction in dilute aqueous solutions. This surface tension reduction will be our property in our quantitative structure-property relationship. Our training set includes 14 compounds for which surface tension of their dilute solutions were known or could easily be measured. Measurements were made using a simple tensiometer. These measurements help train our quantitative structure-property relationship model that will eventually be used to score the inverse design solutions. I am Natalia Shlanimska, a chemical engineering undergraduate student at Tennessee Tech. I've been working with Dr. Biernacki's group. I'm soon to be a graduate student. We're working on shrinkage-reducing admixtures.
Once training data has been gathered, the performance outcomes and atomic signatures are encoded, and a regression is built that relates the structure parameters, which are the signatures, to performance outcomes. This is the quantitative structure property relationship. Then we apply our computer-aided molecular design approach on this training set, and those with the best score from the quantitative structure property relationship model move to the next stage of the approach. Hi, I'm Hamed Kayilo, a chemical engineering PhD student at the University of Akron. My advisor is Dr. Don Visco. After creating and refining the quantitative structure property relationship model, a structure enumeration algorithm is employed to generate structures that are outside of the original quantitative structure property relationship training set. Newly identified structures with optimal predicted properties are then refined based on multiple aspects, including synthetic feasibility, availability, and toxicity, for example.
Hamed identified 26 new compounds from the computer-aided molecular design approach that are predicted to be powerful surface tension reducing agents at low concentrations. Of course, those are only predictions. We now have to test them out experimentally to know for sure. I've used the surface tensiometer to measure the surface tension of 4 of the 26 new compounds and have plotted our performance metric for the new compounds along with that for the training set. We were quite pleased to find that all 4 of the predicted compounds are among the strongest surface tension reducing compounds in the training set, with 3 of them having even stronger surface tension reducing properties than any compound in the training set. Can one of these be a game changer? We'll have to see how they perform in the next stage, in application in cement. So the final step in our approach is to validate if the 4 new compounds can actually reduce shrinkage. To do that, we are starting with cement paste studies, since paste will shrink more than concrete or mortar. Thus far, we've looked at 1 of the new compounds and have found that it closely overlaps with the commercial SRA.
We hope that this video helps you to understand our work, and we're looking forward to report again soon, hopefully with news about new and improved admixtures. See you then.